In mathematics, we often run across problems where we'd like to optimize a solution. In other words, we would like to find a maximum or a minimum. So in this video, we are going to look at some definitions related to maximums and minimums and see a few interesting points related to those definitions. So let's get started here with some extreme values of function, with a section on extreme values of functions. First definition is let C be a number in the domain D of a function f. Then f of C is the absolute maximum if f of C is equal or greater than f of x for all x in D. And it's the absolute minimum if f of C is equal or less than f of x for all x in D. Sometimes absolute maximum and absolute minimum are called the global maximum or global minimum as well. So if you see that terminology, it just means the same thing. Now let's take a quick look at some examples related to this. So for example here, what if we had the function y is equal to 4 minus x squared? A quick sketch of this shows us that our graph looks like this. And what did we just say? We just said an absolute maximum occurs where the y value is the maximum value. Right? So this f of c is a y value. So we have a maximum at c when f of c is equal or greater than f of x for all other x in the domain. So we see at x equals 0 here, we have an absolute maximum at x equals 0. And what is that maximum? Well, that maximum is 4. We can see a similar example over here. Y is equal to x times x minus 1 times x plus 1. And a graph of that equation is here, where it is a cubic that has x-intercepts of -1, 0, and +1. And in something like this, we just see an example where there is no absolute maximum or minimum. So we see that we may not always have an absolute maximum or minimum occur. All right, well, we've got a related definition here, and that is a local maximum and minimum. The number f of c is a local maximum value of f if f of c is equal or greater than f of x for all x near c. So we have a very similar definition here. Oh, there we go. So we have a very similar definition here where f of c is equal or greater than all f of x, but it's all x near c instead of every x in the domain. And similarly, we can have the definition for a local minimum of, oops, this should have said of f, if, and here, of course, f of c needs to be equal or less than f of x for all x near c. All right. And then let's take a look at that compared to the pictures we just looked at above. In this first example, This absolute maximum happens to also be a local maximum. It is also bigger than every x right near there. F of c is bigger than f of x for all x near here. And we see that we don't have any local minimums. In this particular case, while we had no absolute maximums or minimums, we do have a local max at the top of this peak, and we have a local minimum at the valley of this, at the bottom of this valley. So we can see what local maximums and local minimums are relative to graphs, at least. And again, they follow these definitions, although we aren't being very clear on what near means. And really, we just mean for all x in an open interval around c, and that open interval can be as small as we'd like for this to be true. All right, so there's a few other things we want to talk about in this particular video. So let's go ahead and take a look at that. The next thing I'd like to do is write out the extreme value theorem. And that is that if f is continuous on a closed interval a to b, then f attains an absolute maximum value f of c and an absolute minimum value f of d at some numbers c and d in the interval, the closed interval a to b. So what does this mean? This just means if we have a function which is continuous on a closed interval, then we're guaranteed to have an absolute maximum or an absolute minimum somewhere within that closed interval. We get both an absolute maximum and an absolute minimum. Earlier, we saw that on the cubic function, when we take the whole real line as our domain, even though the cubic function is continuous, we weren't guaranteed to have an absolute maximum or minimum. But in the case that we have a closed interval, so we include endpoints here, then if our function is continuous on that closed interval, we will certainly have an absolute max and an absolute minimum. Let's just draw some pictures to see what that might mean. So let's suppose we have a function that looks like this, and we have a closed interval here between some values a and b. If the picture looks like this, our absolute maximum, it looks like, is over here, and our absolute minimum is here. So we get an absolute max at this point and an absolute minimum at this point. Here's another picture. Maybe we get something that looks like this. Again, a closed interval, so we're including these endpoints. Here we have an absolute minimum. And over here at the endpoint is our absolute maximum. So the absolute max or min may occur at the endpoints. But again, if we have a continuous function on a closed interval, then there will be an absolute max and an absolute minimum somewhere in there. Let's take a look at some pictures where an absolute max and absolute minimum does not occur. But of course, for that to happen, we need one of our hypotheses to fail. So what are our two hypotheses? Well, the two hypotheses are that we have a continuous function on a closed interval. So let's suppose that we have a closed interval, but maybe we don't have a continuous function on that interval. And as we can see here, we have no absolute max or minimum, maximum or minimum. Right? This line keeps approaching some point that doesn't exist. Maybe we need to put a point here or something like that to make it actually a closed interval. So whole closed interval for our domain. So here we have again, our function approaching some value down here. But no matter what, it just keeps approaching that value. So no matter what value we pick, we always find something a little bit lower than that. And if we approach this open circle from the right, then again, the same idea. No matter what we pick as a possible absolute maximum, we find that there's a value just a bit greater than that. So we don't have an absolute max or an absolute minimum there. And again, this is because the function is not continuous on our interval. Maybe we do have a function that is continuous on our interval, but it's not a closed interval, so we have an open circle at the endpoint. And again, here we do have an absolute maximum, but we don't have an absolute minimum. And remember, our theorem guaranteed that we would have both, considering if our hypotheses were both satisfied. But here, one of our hypotheses is not satisfied, and in this particular case, we no longer have an absolute minimum. All right, and the reason is, again, that the interval is not closed. All right. And that is where we will end this first video.